So far we have introduced density completely mathematically like this. A random variable x has density f. That means this mathematical condition must be satisfied. Now we want to understand it in a physical way. So if someone gives us this random variable x, can we feel that x has this particular density? Now, as you may be able to guess, any such question has its answer in statistical regularity. So, when I say someone has given us this x, we understand that someone has given us a random experiment, that is a probability space, such that every time we carry out the random experiment, we get one value of x. Say, in order to continue the discussion, I have this f which is a continuous function. I need this assumption because otherwise I will run into problem with non-uniqueness of density. Okay, so what I do is I take the number line, and every time I carry out that random experiment and I get a value of x, I mark that point on the number line. So I do it a number of times. So you can see that the points tend to clutter around this place. So there is higher density of points here and the points are rarer here. Now from such a diagram, it is difficult to understand exactly how more dense the points are here compared to here. So for that we shall use a histogram. A histogram is, you should already know, is a diagram which looks like this, where I am showing the number line as here, and I have split it up into a number of bins or intervals, and I have erected each rectangle with height equal to the relative frequency density of that particular interval or bin as they are called. This is one bin, this is another bin, like this. In case you have forgotten the definition of relative frequency density, it is frequency divided by the sample size and bin width. Frequency means the number of points that has landed in that bin. So in order to find frequency of this bin, I will have to count how many points are there over this interval. I have to divide that by n, the total number of points, and also by the bin width. In that case, I will get some such picture. Now, as is common with any statistical regularity situation, I have to let n go to infinity. In that case, it will be seen due to statistical regularity that this diagram stabilizes. Now, what I will do is I will take that limiting diagram and let the bin widths become smaller and smaller. So I will take finer and finer partitions. Then this step-like thing will start looking more smooth. For example, here I am using big bins. It is really blocky. The bins are now narrower, so it is more smooth, and here the bins are essentially like lines and the entire thing looks very much like a curve. Then this limiting shape will actually give you the density f, assuming that it is continuous. So you see, if you have lots of replications of the random variable, that is, you can run the random experiment a large number of times, you can actually get the particular density. So it is not merely a mathematical abstraction, this is something that you can get from physical experiment. Here is a little MCQ for you. Suppose our random variable x is the monthly income of a randomly selected Indian. So we have a complete list of all Indians and we pick one of them at random, equal chance, and find out the monthly income of that guy. So monthly income may be, say, average monthly income. Suppose x has density fx. Now just keeping in mind the physical interpretation of density, which one of these pictures is the most likely shape for F. So I am showing income here and I am showing the density in the vertical axis.